The real terminology for iron carbon phase diagram is actually iron carbon phase diagram. Why is that so? In an iron, in a liquid form, like as in water, we can add sugar or salt until we reach a point that water can only dissolve that amount of salt. If we want to add more, we call it that before, when it reached the maximum tip, we call that one saturated solution. If you want to add more, keep adding more, keep adding more, keep adding more, what will actually happen? That it will remain solid. It's not going to dissolve. You can do that one by heating the solution. And then when you heat, the water can dissolve more salt. Hence, it creates a super saturated solution. If you put that water back in the fridge or back in there, after a while, you will see that the temperature of the water reduces and the salt it absorbed, it actually spit it out, precipitates it out, and you will end up with that one. This is a reason if you put boiled water in the refrigerator to create an ice and tap water, they both will convert into ice. But one ice is going to be crystal clear ice, other ice is going to be tap water ice is not going to be crystal clear. Yeah, because of the minerals absorbed in that one. Okay, now different phase, I will explain that later as well. This is gamma, like an alphabet R, Greek letter. We call that gamma iron. Gamma iron is an austenite, is also known as austenite, is a form of FCC, face center cubic iron, with a maximum, that is solubility, SOLB is solubility, of carbon 2% at 1150 degrees centigrade. Where I'm getting all these values, I will explain. Then we got the alpha iron. Alpha iron, this is the symbol, alpha iron, also known as ferrite, one of the softest form of iron. It's a BCC iron with a maximum solubility of carbon 0.02 at 723 degrees centigrade. Some books 721 degrees centigrade. Then we got a thing known as delta iron. Now delta iron, this is the symbol delta. Sometime this is known as small delta. Why it's called small delta? Because it's exists for a very short period of time. Yeah. Delta iron is a form of BCC, body center cubic iron, with a maximum solubility of 0.1 at 1492 degrees centigrade. It exists between 1400 degrees centigrade and 1538 degrees centigrade. On an iron carbon diagram, it's actually a very tiny region. Okay. Then we got cementite. Yeah. Cementite is a chemical compound. As I mentioned earlier, salt in water. Carbon, iron can absorb 6.67 percentage of carbon. The more carbon you put in, iron is not going to absorb that carbon. That carbon will remain inside as a chunks of carbon. It's never going to absorb. You can heat it, do whatever you like, it's not going to absorb. But when you cast this iron, the iron is going to be casted, and then there is some tiny inclusion, and that inclusion, when you apply the force, that is a weak point stress concentration, because carbon is soft as compared to brittle as compared to steel or iron, so it will break. So that's cementite. Cementite has a formula. I will write it in a minute. If Fe3C, I will write later. Then we got the pearlite. Pearlite is a fingerprint structure. Pearlite is, it's look like that. That's a graph. Pearlite is actually made of two phases. It's made of two phases. One is called the ferrite, and the other is cementite. Ferrite and cementite combine and form that one. In here, if you can actually see the white lines and the black lines, yeah, the white lines are the ferrite. The black lines are the cementite. Cementite is very hard, very brittle. On the other side, ferrite is very soft. Cementite, and it contains around 88% of ferrite, so a lot of soft phase, and a little bit, which is 12% of the cementite. That's the composition of pearlite. Yeah. Then we got the ladyburite. This is how the structure of ladyburite is. Now you can actually see the white and the black, white and the black. Now here, the white one is the austenite. Yeah. So here the white one is the austenite. So it has the austenite, and the black one are the cementite. Yeah. So austenite and cementite. Laterite is a lot harder than pearlite because it contains more cementite. Yeah. Okay. Now then we got the reactions. One reaction is called eutectoid reaction. Yeah. Eutectoid reaction is a reaction where one solid converts into two different solids when you cool it down. Yeah. I will explain that later. Then we got the eutectic reaction. Is a reaction where a liquid converts into two different solids, solid 1 and solid 2. Yeah, I will explain that one later. Okay. So any questions so far? Okay. This is an iron carbon phase diagram. Yeah. On this side, it's 100% pure iron. On this side, it's cementite. Here, you got 6.6, 100% cementite. What is cementite? Cementite is 6.67% carbon. So that is 6.67%. After that one, why don't we go all the way 100? It's we don't study the phase diagram after that for iron carbon because that's so brittle that we don't use it. Okay. This region is known as single phase region because there is nothing else in this region. It's only austenite. Yeah. Now let me just copy this thing. Thing is, we know this is gamma iron, single phase region. We know this boundary is cementite, Fe3C. That's the formula for cementite. So this side is cementite, Fe3C. This is pure iron. Okay. This is alpha iron, known as ferrite. So ferrite occurs in this region. Yeah. Then this is a symbol for ferrite. Now, if you have a look at that one, this is the delta iron. Only exists between that and that temperature. This line is 1150 degrees centigrade. This line is 723 degrees centigrade. Yeah. Okay. Now, this percentage here, all the way down, is 2%. If you want to do the heat treatment, this is what you do. Let's say I got a 1.5% carbon steel. So 1.5% carbon steel is here. I heat it up. When I heat that thing up, what will happen? See, I'm increasing the temperature. It goes here, so it has this combination, alpha plus that one. But how do I know it's got this combination? I will explain. So it has to enter the single phase region. These lines are known as A3 line. This is called the A1 line. Yeah. So in engineering, they ask you to can you heat it up 50 degree above the A3 line? So you know, like it's 1.5%. So you know, oh, so it has to be that temperature. Yeah. It has to be 50 degree above. Yeah. Okay. So you can do that one. Now, how do I find out what are these things here? So first thing is, let me just highlight that one. You need to know this is alpha. You need to know this is gamma. This line here is known as liquidus line. Why? Because above this line, everything is liquid. So this line is known as liquidus line. Then we got a line, blue one. This line is known as solidus line. This blue line. Why? Because everything below that line is solid. Yeah. Let's say I have no clue what's here. I don't know what's here. So how you find out? You know that's gamma and you know that's cementite. So draw a point. It touched the gamma. So there must be some gamma here. It's cementite. So here in this region, it's gamma and cementite. Yeah. That's how we find out. I want to find out what's here. Let's say I don't know what's here. So what I do is I put a point here. It touches alpha. So there must be some alpha. It touches cementite. So there must be some cementite, Fe3C. That's how we fill this gap. If the point is here, it's more closer to the cementite. Yeah. Alpha and cementite. But here more cementite, less alpha. Yeah. So this material here is going to be a lot harder as compared to the material here, which you can see 2%. More harder, more brittle. Cementite is brittle. I want to find out what's here. alpha, liquid. This liquid consists of iron plus the carbon as well. Yeah. Okay. I want to find out what's here. Cementite, and the other one is liquid. Yeah. I want to find out what's in this tiny region, alpha and the liquid. Yeah. So now you know how to find out different phases, how to fill up that one. And I know the temperature is 723 and that one. Now, when we look at the austenite microstructure look like this. The structure of the austenite is a single phase region. So this is how it look like. Yeah. When we cool it down, this is at this temperature. When we cool it down at this, I'm going to call it 1. I'm just cooling it down this line. This is the line I'm trying to cool down. Yeah. So I have, let's say, 0.75. Yeah. So I'm just trying to cool it down here. So I'm falling at 0.1. This is how it looked like. When I cool it further here at 0.2, this temperature is still exactly the same. But as soon as I cross this line, yeah, what will happen in this region? What will happen? I have the austenite. How do I know? Because look here, austenite. The austenite start converting into alpha iron. The alpha iron start to form. So the microstructure here at 0.3 look like something like that. So there will be some austenite. Yep. But then I'm just going to use red color. Then a crystal of alpha iron will start to form. And as I go from 3 to 4, 4 is somewhere here. Yeah, the 0.4. Yeah, these crystals will become bigger and bigger and bigger and bigger. So these are ferrite. The red ones are the ferrite. Yeah. As soon as they enter here, this point, let's call it point number 5, this region, after this line, below this line, austenite does not exist at all. What does exist here? I don't know. So I just draw a line here. Oh, austenite. No, sorry, cementite. And here, alpha. Yeah. So then here, the structure is going to look like this. This structure will have only alpha iron and cementite. So that will be your fingerprint structure. Yeah. Yeah. Where you will have a cementite, a white cementite inside, and you have the black austenite. Yeah. And the whole stuff, we call this one as pearlite. Pearlite is a fingerprint structure. Yeah. Happy with that? What happen if I start cooling? I follow this line. Let's say, what happened if I follow this line? Here I got alpha. At this 0.1, I got alpha. 0.2, I got alpha. But when I cross this line, this point, yeah, it's either the eutectic point or eutectoid point. Yeah. So one is called eutectic here, and then that point is called eutectoid point. So here, this is one solid. What is one solid? Gamma. Yeah. So here, the gamma. But when I reach that one, what is here? What's here? Alpha and cementite, isn't it? So this point, a gamma converts into alpha plus cementite. So this is one solid converting into two different solids, solid 1 and solid 2. And where does this happen? This happens at 0.8% carbon, and at 723 degrees centigrade. See, 0.8% carbon, 723 degrees centigrade. Yeah. Now, what is that point then? This one. Let's have a look at this reaction here. If I cool it down, this is liquid, this is still liquid, still liquid, still liquid. But as soon as I go here, one liquid converts into two different solids. What are two different solids? This and that. Yeah. Okay. Iron has its really good properties. So why don't we keep austenite at the room temperature? As you cool down, austenite will convert. And suddenly I will quench it. So I won't give enough time to convert